Hello, and welcome to Pyramidal, a Twitch and YouTube show where we learn how to build a modern distributed database for online transaction processing. And when I say transaction processing, I have a very specific thing in mind. I don't think about general purpose data manipulation where you apply customer supply functions to compute whatever. No, I am thinking about a very specific workload, which is characterized by transactions across multiple objects at the same time, which generates high contention and which prevents horizontal scalability from actually being any more effective than just running on single thread. And one prime example of this kind of workload is financial transactions. So that is what Tagabitl is, and that is what this stream is about. How to effectively process transactional workloads using modern hardware, using silicon rather than clay, which we used for pretty much the same purpose 5,000 years ago, or even more. Well, I think even more. It was like about 8,000 years ago. Okay, so we had 2 weeks break because I was in South Africa on top of a Table Mountain, because if you are building databases, you gotta be on the Table Mountain. But we are finally back. And what are we going to look at today? Well, let's check our exciting to-do list. Okay, so someone on YouTube commented that I have a way too small font size, and they were 100% correct, because I had this commented out in the last episode and maybe for a few episodes before that. So apologies for that. Hopefully it is fixed now. Okay, so our to-do, and I think I know what are we going to do today. Well, this one we actually done, and today we finally start with queries. The bulk of transactional processing are the read, modify, write operations. And this is what is hard to scale for 2 reasons. One is because of read, modify, write, you have contention. You cannot just shard read-only data across multiple read replicas. You like have to actively manipulate the data. And because of writes, you cannot cache the data. As soon as you accept new input, you have to durably persist it. And that creates the fundamental bottleneck of the system. Just how fast can you write data to your local SSD? Queries, in contrast, is like read-only operation. We don't modify the data, we only read it and compute the result. So they are relatively easy, and as of today, they aren't actually the strongest point of TigerBeetle, but still we have support for some query capability, and today we are going to dig into this support. So I want to warn you that this is going to be like brutally unstructured series of episodes, because I have absolutely no idea how queries work inside a database. So I'm going to learn this together with you, and mostly it's going to be like, me looking at the code and like not understanding what's happening. So to make this like painfully obvious, we'll start we'll start from the very start. We'll start with looking at the TigerBeetle docs, because I mean I'm so bad at queries that I don't even know where our so it was subdomain. Okay, because I don't even know where to start. Okay, let me flip this to nope. Let me flip this to night mode. Yeah, much better. Oh wow, that's a nice color scheme. Okay, so I think we are going to. I think I am looking for transfer account filter, query filter. Okay, request query transfers. So this is an example query which we are going to study how it is implemented. Okay, so let's see query transfers. Query transfers by intersection of. Okay, I think I want embiggen this a little bit. Yeah, query transfers by the intersection of some fields and by timestamp range. So we pass in a filter and we expect to see a possibly empty array of transfers that match the filter, sorted by timestamps, always limited in size. If there are more results, you need to page through them using query filter timestamp mean and timestamp max. And that's actually already interesting. So remember, TigerBeetle is a database which doesn't do dynamic memory allocation, or every byte of memory is allocated at the startup, and we just reuse that memory throughout the operation of the database cluster. This isn't actually the goal. The goal of TigerBeetle isn't to do static memory allocation. The goal of TigerBeetle is to have tight limits on everything, on every resource. If there are, like, more than one possible thing, for example, more than one query result, TigerBeetle always has a very specific upper bound saying, like, hey, this is how many results are allowed. Translating this philosophy to query. A query in general could return unbounded number of results. Like, it might be like 0 results, might be 10, might be 10 million. And obviously, this kind of like doesn't fit in this paradigm, or at least doesn't like immediately fit in this paradigm of everything is bounded. And if you are not thinking through your limits, you might write a system which says, okay, I'm going to like open TCP connection, and I'm just going to stream all the results as they come in. And like if someone writes a query which returns all 5 petabytes of my data, okay, I'm just going to stream that through TCP. And obviously, I mean, that's not gonna work. Like, you know, probably your connection will be severed before you stream out of all the data. Or more likely your database will get overloaded. So there's going to be some physical limit which will kick in. But if you don't explicitly code that limit into your database, you wouldn't actually know what that limit is. For Tagemittal, recall that every communication, including query results, is handled through this message type. And the message is a buffer of message size max bytes, which is, I think, 1 megabyte. Yeah, 1 megabyte. So we have kind of like physical limit, and that is 1 megabyte of a message. And that means that, hey, like no matter what the query we will write, we could only get 1 megabyte of output out of it. Okay, so how do we reconcile that limit with the fact, objective physical reality, that some queries might return a lot of data? Well, the answer here is that we will always return results sorted by the timestamp. Recall that at Tagemittal, we use timestamps as our internal synthetic primary keys. So the user identifies a particular account or a particular transfer using large ID, 128 bits, but internally we convert that to timestamp. And we make sure that timestamps are globally unique. There are no two accounts, no two transfers, and no account transfer pair which share the same timestamp. So that means that sorting by the timestamp is never ambiguous. And that means internally, in turn, that when we return queries, sorting by timestamp can initialize this result. What's more, you could say that, hey, if you queried a lot of transfers, and like say there's like 10 million results, we are going to return the first 1 megabyte of the result, and then you could query for the rest using timestamps, because in your query you could additionally constrain your set to only look at the specific timestamps. So that is the trick. You have a problem whose mathematical formulation evokes the notion of infinite set, or at least arbitrary large set. Like, you know, what is the result of the query? Well, worst case, the result of the query is your entire database. Then you reconcile this with a physical reality that you cannot actually achieve infinity, because your resources are finite. And even though there are like plentiful, like there are big machines, there is big iron, they are not free. So you want to frugally use your resources. And the way you reconcile this too is by thinking through your API design and making sure that each individual API call operates only on fixed amount of data. There is a small upper bound, like a megabyte. But also you make sure that if you need more than that, you could string several API calls together to get the results you want. Also, what really happens here is immutability. Because, actually, okay, this is fine. So, another load-bearing thing here is immutability. Once a Tagemittal transfer is created, it stays immutable. So if you are paging back in time, then you are guaranteed to see the full sets of results. Oh, yeah, I think the opposite is true. That if you are paging forwards in time, you also would be guaranteed to not miss any transfers, because in addition to uniqueness, tag capital guarantees strong monotonicity of timestamps. So what I'm saying is that, okay, let's say that you queried a bunch of transfers and you get, say, like 5 transfers. But just after your query was executed, a new transfer was submitted, which would also match your query. So the result is correct. At the point when the query was executed, according to strict serializability, you get a complete set of results. At the same time, right now, there is actually one more result. But if you use the maximum timestamp of what you received previously to do a new query, you will get that new transfer. So that's actually pretty tight. Okay, let's see what is a query filter. So we could okay, do we have a description of how query filter actually works? No, but I think the way this works is that if a corresponding field in the filter is set to 0, so for example, if you set user data to 0, then you just won't be matching on this field. So you will allow like any user data. But if you say user data equals 16, then you will be only looking for transfers with the matching field. So query filter is essentially an AND of all of these operations. So these are filters. Set 0 to, oh, no. This is the commented optional. Set 0 to disable the filter. Okay. Then we have timestamp min, timestamp max. Then we have limit to, like, if you don't need all 8,000 results, usually, so message size is 1 megabyte. Size of a transfer is, I think, 128 bytes. I always forget this. Yeah, size of the transfer is 128 bytes. So there is about 8K transfers we can pack in a single query result. But if you know that you need less than that, you could specify the limit. So we have flags reversed, flag reserved, which is kind of like confusing. Also, why we... Okay, there is a typo. Flags reserved. Let's fix it. Let's go and fix it. Okay, query filter. Query filter.md flags, and let's check if it's in account filter. Okay, yeah. Let's flags linked. Okay, yeah, we do set flags. Okay. Doc consistently name individual flags in the docs. That's typo. Okay. Okay, back to our ship, as they say it in Russian. Okay. So okay, I think this is pretty clear. So you submit a query to Dragonbeetle and you say, hey, I want to get a bunch of accounts, and you control timestamps of the accounts, like the time range where your query applies. Then you control which field values are you interested in. So you might look. So for example, I think, do we have? Credit debit account. Wait, what? We aren't. Huh. We can't filter. We can't filter by account ID. Haha, this is fun. I was assuming that we could do things like get all. Well, I think. Is this lookup transfers? Okay, so I'm confused. What I'm confused about, let me tell you so that you're also confused. So you see in the fields, we don't actually have debit account ID, credit account ID. This is surprising. I would expect that we should have, have a capability for querying all accounts all transfers belonging to particular accounts. But I think this is actually a different, there is like, wait, no, lookup transfers, get account. Okay, yeah, for account transfers, we actually have a separate okay, yeah. When we want to query for a particular account, we do, for some reason, have a separate query, which I don't honestly fully understand at this point just yet. And I guess this is, well, it's not interesting. Well, okay. Maybe it will become more obvious, or at least less obscure, why we need both of those. But if we start with query transfers, let's see how query transfers work. Okay, so that's the docs. Let's see how this is implemented. So we have transfer in our Dragonbeetle, and we have query filter, which matches what we are filtering. So user data, ledger code reserved to timestamps, limit, flags. Okay. And flags is reversed. Wait. Okay, I am. Oh, so my pull request actually is incorrect. Oh no. Okay, let me quickly convert it to draft while Raphael's not watching. Flags. Oh no, it actually is correct. So reserved. Okay, so reserved here. Timestamp min, timestamp max. Query filter. So I think the docs were actually correct, but the order, what confused me is the order. So reserved here, filter. Reserved is before timestamp in account filter, and in query filter, reserved is also there. Okay, so Okay, so let's then do this. So code reserved and account filter code reserved timestamping. Okay. So let's do reward. Looks consistent or fields in filter and account. I got confused reserved in filter. Oh, this is embarrassing. Being specified after flags. I think order in account filter is better. It matches source order. The flags are last, so you don't have to pay attention to nesting. Get to dsum big weight between a flag and the field. Oh, okay. In my defense, I'm reading docs on the stream. So it is only fair if I'm not exactly correct. Why? What? This annoys me a little bit. Why there isn't a nice way to do that? Okay, should be better. So okay, where were we? We were looking at the implementation side of things. Okay, so query limit flags. Yeah, everything we've seen, and the only flag we have is reserved. Reversed. Okay, so the next thing is that we are going to have an, oh no, it's actually in the same file. We are going to have an operation which says query transfers. Do we have batching in our to-do? Out batch. Okay, we do have. Oh dear, I feel like I feel like the team is able to write code faster than I'm able to cover. So perhaps my hope to one day finish Iron Beetle is in vain because there is like more and more stuff I get rid of. Okay, so anyway, we have query transfers. Okay, this is the iteration. Okay, let's see. State machine prepare. So remember, we have prepare part, which just assigns the time, and execute part. Well, prepare, which assigns the timestamps. When we have prefetch, which goes to disk to fetch the data, and then we have Then we have execute, which actually does CPU processing. And for normal transaction processing, like actually applying transfers, the cool thing is that given a batch of 8,000 transfers, you could read from disk everything all at once because your data accesses do not depend on the logic of your transactions. You can predict data access perfectly. But then the actual execution, due to contention, is best served by a single thread. Okay. So let's see. So it's our operation multi-batch. Query transfers. So our operation is multi-batch, so we aren't going here. Wait, our query transfer is multi-batched already. Maybe we'll have to cover multi-batch, but I don't want to. I haven't prepared. I haven't prepared for multi-batching. I'm going to do multi-batching, but I don't want. Okay, so let's. Okay, so I will try to skip multi-batching, but this isn't cheating because I also don't understand what multi-batching does. And that means that, okay, if I will able to understand it without understanding multi-batching, then so you will. If I won't be able to understand it with multi-batching, well, I guess I will have to understand multi-batching first. Okay. So yeah, I guess, yeah. Okay, so, but the general idea is that we need to advance timestamp according to the number of events. So for the case where we do create transfers, if we create 100 transfers, we must adjust the timestamp by 100 nanoseconds. If we create 1000, then we need to advance timestamp by 1000 nanoseconds. So I think for lookup transfers, we don't actually, that's cool. For lookup transfers, we don't actually advance the timestamp, and that means that several consecutive lookups might logically happen at the same point in time, which I think is actually fine. Okay. So we prepared. That's easy. Now prefetch. So, okay, yeah. Going back to this prepare, prefetch, execute split. What's like in the hot path, in the write path, the invariant is that prefetch does all the input output and execute does all the computation. For queries, I think we actually are going to mostly do all the computation in the prefetch path. And then execute will just memory copy the data out. But well, we'll see. Maybe I'm misunderstanding this. Okay. So we have scan lookup buffer index, scan lookup result items, and so this is something I know. I know that scans are somehow related to queries. So we'll see how this works out. Eventually, it's not going to be easy. It's not going to be fast. Okay. So we have prefetch input. And then prefetch query transfers. So we go and get prefetch query filter. How do we get prefetch query filter? Byte slice. Wait, what is? Hmm. I actually wondered. Huh. Okay, so Raphael wrote this function. That's nice. I actually wanted to have something like this. Go. So size, precision, exact, inexact. Casts the result. Okay, so we return either the or const. Okay, so this is const query filter. Okay, that's good. And yeah, this is a multi-batch, so we get several filters. What's filter index? Okay. Okay. I don't like this. Kind of like I would maybe assert actually that we haven't exhausted this, but like whatever. So okay. Prefetch input. Prefetch input is something which is applied by a multi-batching, right? Wait, I don't understand. Oh, yeah. Okay, so this one. So prefetch input is if operation multi-batch. Then we go and okay, I don't understand this, but I guess it's fine. I don't have to understand all the code, right? What could go wrong? So, oh, right. Well, no. So, prefetch input is all the filters, and then we select a particular filter using the scan lookup results items. And what is scan lookup results? It is array list and managed. What does it stores? No idea. Okay, so get prefetch query filter. Okay, prefetch. Then we go and prefetch query transfers scan. Okay, we have the scan points into prefetch input. Going to get a scan from a query filter, and kind of like, why are you doing this to me? I obviously want to fold like this thing, not round parentheses. Okay, so if we get a scan, we do return. Otherwise, we do something else and prefetch scan resume. Okay. Actually, was it? Fetch query transfers. Fetch query transfer scan. Okay, so what is get scan from query filter? Aha, so this apparently, I think, is constructing that like program which we are going to execute while we're executing the query. Because like query is like, like really a stream processing program. We have a bunch of trees which store sorted values. And what you're going to do is that you're going to run like a sort of like merge sort over all of the streams using like, a reading head with like a little program inside. And the reading head will like, look at a little window and see an element from each stream and then decide either to toss it away or to add it to the output. And I think this is the place where we are programming this reading head. So we check that the filter is valid. If the filter is not valid, then return. Now, otherwise, we get filter direction. We get filter range. Field enum query filter. User data. So for each filterable field, we are going to add it to a scan condition. So scan conditions is itself bounded array of scans. So scan prefix, scan builder, scan timestamp, scan merging section. Okay, so I sort of I feel like I need to understand what the hell is scan builder. Well, scan builder, it has scan scan builder type. Scan builder. Yeah. So this actually starts like the mid of a query. Scan builder. So what is a scan? So again, kind of like scan builder is a helper to creating and combine scans using any of the groove's indexes. Instead of a single groove per scan type, introduce the concept of orthogonal grooves. For example, indexes from the groove transfers and parent transfers can be used together in the same query, and the timestamp they produce can be used for lookups in either grooves. Okay. Never mind. Probably will become clearer later. Okay, Groove storage. Scan builder, scan. So yeah, if we end up doing some refactors, then let's do what we consider idiomatic. Scan tree. So we have a pointer to scans, and this is actually okay allocated. What is scan max? Scan max is 6. And what's a scan? Well, it's scan type, and what's scan type? Yeah, so this is so scan is dispatcher. What's dispatcher? Oh dear, we are okay. We have scan buffers, scan builder, scan fast, scan lookup, scan merge, scan range, scan states, scan. Okay, huh? I feel, folks. I feel, folks. This is going to occupy us for a long time. Okay, nothing makes sense to me, but that's normal. So okay, scan builder holds an array of scans with a count of scans, and it also holds merges. Aha, so apparently, okay. It kind of like starts making sense to me, maybe not. So, yeah, I think what we are doing here is a stream processing. Our data is stored in a sorted form on disk. So using only O1 memory, we could read petabytes of data in a streaming fashion. So like the core abstraction is like a stream of value which are sorted. Now you could actually, and that's a scan. Now what you could actually do is that you could take two such streams and like merge them, like using union or intersection or like any other stream processing combination. And this outputs a new stream of values. And that is that kind of like, that new stream of values is essentially a view into two underlying streams. So the scan, so the scan tree is presumably like the physical scan of the trees. And merges, we could, like, they're like virtual, they don't actually consume resources. But we always merge two, so we like do binary tree. So okay, this is kind of like makes sense. Maybe, probably. Okay, we allocate scans. We allocate mergers. Okay, then we destroy scans, destroy mergers, assign and define to self. This looks legitimate. Okay, this is also in place initialization. Let's see who actually stores scan builder. Is it state machine? Scan builder. Okay, so scan builder actually belongs to a grove. And that probably means that a grove can have only one scan active at a time. Okay, where are we? Like scan, get scan from query filter. So, okay, how are we going to use this thing? So we are going to create multiple scans. Scan timestamp, scan merge intersection. Okay. Okay, reset. Kind of like does nothing really. Which is surprised. Why would we need reset if we... Oh, no, because it actually resets scan count and scan count and merge count to 0. Okay, that makes sense. Challenge a scan of the secondary index specified by the index, searching for an exact match in the composite keys prefix. Produces the criteria equivalent to where field equal value. Results are ordered by the timestamp. Okay, scan builder, scan buffer. What is scan buffer? Is it key prefix type? Oh dear. This is hard. This is not what I signed up for. Well, okay. We'll do. Okay, so we create scan impulse, scan add. We create a scan. Okay. Scan timestamp, merge union. Okay, so I think like scan add and scan merge or merge add is what we're doing. Okay, scans among succeeded. Oh, this also can error. Okay, likely there's only one error, but still. Scan dispatcher union init, scan dispatcher. Okay, so how are we using this in the state machine? Well, okay. Merge intersection. I think this is interesting. So yeah. So I guess what the code is doing is that it's saying, okay, if we have like, we want field A to be equal to 2, field B equal to 3, and field C equal to X, we have first 3 scans for field A, field B, and field C. And then we additionally do this merge. And merge actually is not necessarily binary. It might merge several scans together. Okay. So that's kind of like makes sense. Scan timestamp. Okay, so scan timestamp is probably the easiest. Okay, I'm wondering, should we dive deeper into scan and scan builder? Probably not yet. But okay, let's see. Yeah, let's for now keep our focus on the state machine and see like the high level control flow. So okay. Anyway, we kind of like we get a scan from the query filter. So this internally is kind of like a tree of, so a scan is like sequence. Internally, it might be actually like, you know, computed as a merge of several underlying sequences. But what we get as a result in a nice object-oriented API is the sequence. Okay, I don't want to prefetch query accounts. I want to query transfers. So we have the scan. And then we have scan lookup buffer. So why scan lookup buffer? I have no idea. Okay, I think this all interacts with multi-batching pretty significantly, but oh well. Okay, scan lookup. Wait. Well, okay, so we got the scan, then we scan lookup read, and then scan resume. Okay, so we kind of like running this prefetch in a loop. And I would assume that yeah, it kind of like this thing like copies the data into the scan buffer and then calls our callback. Okay, so okay, I have no idea how this works, but I think that as a result of this prefetch thing, we actually will have the actual results in this scan buffer, and the scan buffer is going to be here. Okay, so that means that prefetch is doing like all the heavy lifting. So let's see how execute works. I think execute should only essentially copy data. Well, not execute query transfers. Yeah, okay. So the actual execute is just copying the buffer. Okay, yeah. So I think this is maybe a good spot to stop. So I think, well, I'm not sure about you, but what I do understand, I understand the public API that TinyBeetle provides. Like, you know, you could query objects and filter them down by several fields, and you could like query intersections of those fields. And I understand that the way this works is that all the actual work of scanning happens during prefetch, and execute is just memory copy. Why do we need memory copy here? Could we avoid memory copy? Maybe, probably. Maybe we will optimize it. And the actual scan is going, okay, actual scan is going to be hard. It's going to be like simultaneously dynamically dispatched thing, but also comp time parameterized thing. So yeah, that's going to be painful to wrap my and your head around. But well, we'll manage. Luckily, this is a problem for next week Matclat and next week you because we are at an hour and we are wrapping up. But next Thursday at 5 p.m. UTC, live on Twitch, and then of course on YouTube on Tiger Beetle's channel, we will continue studying the scans. I'm excited. This is curious. This is like the last big part of Tiger Beetle I don't understand. Although, as I've said, I fear that by the time I do understand scans, there's going to be a different part of Tiger Beetle which I will not be understanding. Okay, that's it for today, and goodbye. See you in a week.